Welcome back. So we talked about the notion of memorization in deep learning, and basically the definition was talking about the sensitivity of models' prediction to the removal of individual data points from the training set. So in particular, the definition was the probability that we are making a correct classification when a specific image is in the training data minus the probability that we are making a correct classification when we exclude that sample from the training data. If this difference is basically near zero, that means that it doesn't matter whether the sample is in the training data or not. We can correct these labels near perfectly. On the other hand, when the difference is near one, then that means that there is a significant change in the model's performance when the sample is removed. So therefore, we must have memorized it due to our good performance on the sample. So therefore, we are talking about some notion of sensitivity here. And if you recall, in our lecture on privacy and differential privacy, we also talked about sensitivity. We basically said that when we talk about the notion of neighboring data sets, right? We basically said that the performance of our model or the output of our mechanism does not change much when I consider two neighboring data sets, okay? So therefore, a natural question is about the relationships between notion of memorization and differential privacy. For instance, if I say that for a specific model and a specific learning algorithm, I have some differential privacy guarantees, what does that tell about the memorization scores of different data points in the training data? Okay. In fact, there is a recent result in the literature that basically is saying that if your algorithm is epsilon delta differentially private, for instance, again, could be DPSGD, differentially private stochastic gradient descent, where we would inject some noise into the learning process by perturbing the sample gradients. So when we have epsilon delta differentially private learning algorithms, then with high probability, with probability 1 minus delta, the memorization score is bounded by 1 minus e to epsilon for all data points in the training data. Okay? So therefore, the theorem states that if you have differential privacy, you have low memorization tendency. Okay? A good question or another question is the other direction. So if I have low memorization tendency, can I make a claim that the differential that my learning algorithm was epsilon delta differentially private? This is I would say an active area of research. So we don't have like a good answer to this question right now. Okay, but nonetheless, this theorem seems to imply that differential privacy is stronger than low memorization. All models that have that are differentially private have low memorization tendency across all data points in the training data as well. Okay. So essentially, as the privacy parameters go down, so epsilon gets closer to zero, delta gets closer to zero. That means that we have a stronger privacy guarantees. And this memorization, this theorem states that e to the epsilon goes to 1. So that means that with a very high confidence, we are saying the memorization scores of all data points in the training data is near 0. So it means that we are not memorizing them, or our model does not memorize those samples. Okay. So this again highlights, this result highlights the privacy accuracy trade-off. Okay. So in particular, the higher privacy guarantee you want, the more you have to sort of trade accuracy. Okay. So more specifically, in the long-tail data distribution case, where as we talked about, memorization is essential. If we are imposing very strong differential privacy guarantees, that could hurt the performance, because a strong differential privacy guarantees means very small epsilon, very small delta, such that according to this theorem, memorization score is very, very low. So it means that we're not going to memorize samples, That's not an issue if the sample has a high frequency in the training data, but low frequency data belonging to subpopulations that are small are not going to get memorized well. So according to the results from the first part of this lecture, that means that we're not going to do well in terms of generalization and therefore performance. Okay. So that's basically one connection I want to make between differential privacy and memorization through this lens of sensitivity. Okay. But this sensitivity is also something that we can leverage for other purposes. Okay. For instance, the definition of memorization that we mentioned, as we said, quantifies the sensitivity of the model prediction with respect to removal of individual data points from the training data. Now, this is a metric, right? So you can talk about, okay, for a specific data point, a specific model architecture, what's the memorization score of let's say a specific cat image. And it turns out that this is very, very time consuming to compute. And so that's sort of one drawback of this definition, if you will. But there is also this drawback that, as we demonstrated, the definition is not able to distinguish between truly hard examples and the noisy examples. Okay? And again, this is crucial because we don't need to generalize to noisy examples, but we need to generalize to truly hard atypical examples. Okay? So ideally, we want to make this distinction, get rid of the noisy examples, or maybe correct their labels, and then train our model. Okay? So therefore, we need basically, first of all, computationally efficient proxies, okay, to memorization. And secondly, hopefully we can make sure that these proxies can make this distinction between truly hard as well as mislabeled examples. Okay. All right. And obviously, or naturally, our tool here is to leverage ideas from optimization for deep learning. Okay. So we know that we are minimizing the training loss. So our main tool to train a model is through minimizing the training loss, solving an optimization problem. So if we are interested in characterizing the sensitivity of a model to individual data points, you could talk about the sensitivity of the training loss to individual data points. Okay. So therefore, you could characterize sensitivity by looking at the loss and its variation with respect to individual sample Z, as opposed to the parameter W that we are optimizing over. Okay. Formally, there's this nice definition in recent works that tries to characterize sensitivity by looking at what is referred to as the curvature of the loss with respect to individual samples. Formally, it is defined to be as the trace of the Hessian of the loss, not with respect to W, okay, but with respect to Zi. So for instance, if you were to calculate this in practice, you have an image. So Zi is basically an image with features Xi's and labels Yi's. So what you need to do is to basically find the second derivative of the loss with respect to Xi, okay, and then take the trace. Right. So I'm going to talk intuitively why this is something intuitive and potentially useful, but mathematically we have this theorem that I'm not going to go over its proof, that states that under certain assumption we can actually relate the memorization score, this elegant definition of memorization score, to this notion of curvature. In particular, the relation is something like an affine relationship, which is also verified numerically in the literature, where under these assumptions, the memorization score is upper bounded by some constant A times the curvature plus some small constant B, such that when the curvature is small, we can say that the memorization score is also small. Okay, and when curvature is large, we can say that the memorization score is also large. So therefore, we could potentially use this curvature as our memorization proxy to talk about basically which samples are memorized, which are not, and hopefully later on leverage this to make a distinction between truly hard samples that need to be memorized versus noisy samples that are not essential and could be removed or need to be identified and corrected. All right. So, but why this input loss curvature? Okay. So, in particular, curvature captures the local structure of the loss landscape. Okay. And again, we are talking about sensitivity. Okay. So, when let's say the sensitivity with respect to a specific image is low, we can kind of imagine that that image lies in a very, very flat region. Okay. So again, flatness and curvature is something we've talked about before in the context of optimization, and that captures, that is sort of quantified by looking at the second order derivative or Hessian in the case of multiple dimensions. Okay, so therefore, when we are sort of in again a sample that is typical, and our model or loss is not too sensitive with respect to that, we can imagine that in the input space, sample lies in the flat region of the loss landscape. Okay, versus, and again, this is basically we have more supports in the training data, so it could be basically a typical example. On the other hand, when the sample is atypical, it could lie in sharp region of the loss landscape. Okay. And crucially, when I say loss landscape in this context, I'm not talking about the parameter space W. I'm talking about the input space Zi. Okay. Now, what we have done here, we've actually went ahead and calculated these curvature scores, if you will, for different images from the ImageNet dataset, and we kind of visualize whether they look like typical examples or atypical examples. And as you can see here, low curvature training examples from the ImageNet are kind of examples that are typical of their class. So they're kind of easy for the model to learn and predict the label. On the other hand, images that have a high curvature score from the training data are those that are atypical and could also be those that are potentially noisy. Okay. So therefore, it kind of makes sense, both intuitively, as we talked about in this slide, to relate or to characterize memorization through the lens of curvature. And also, we have some mathematical backing of this intuitive idea. Okay. So at first glance, it's not clear. I mean, this is again has some affinity with memorization, but it's not clear whether it is something useful or not. So I'm going to talk about that in a moment. But before that, I want to make this comment that in practice, what we observe is that if we look at the accumulated curvature throughout training, as opposed to the final curvature, which we were talking about, then we can see a higher correlation or affinity between curvature and memorization. So therefore, in practice, a recommendation is to look at, again, the accumulated curvature throughout training to make sure we have a really good proxy to the memorization score. Okay. All right. Now, curvature, as we talked about, depends on the Hessian, and Hessian is a second-order quantity, second-order derivative, and intuitively, it's a quantity that seems to be very, very difficult to calculate. Okay. So at first glance, this curvature seems something that is also computationally infeasible to calculate in practice. However, it turns out that we can find a really good approximation to the curvature. First of all, we don't need to calculate the Hessian. All we need to calculate is trace. Okay, And there is this elegant result in the numerical linear algebra literature that uses a randomized trace estimator called Hutchinson trace estimator. So we can leverage that. And also, instead of the curvature, we can sort of use curvature squared to kind of, again, capture the notion of sensitivity. Okay. So all in all, so including, again, like the curvature square, Hutchinson trace estimator, as well as using zero-order gradient estimation, we can find a really good and efficient approximation of the curvature, something that I'm demonstrating here. Okay, so therefore, curvature square is basically proportional to this quantity. What is this quantity? So it says that you sample m random perturbation vectors that come from some distribution, could be Gaussian, could be Rademacher distribution, and this is sort of required to use this Hutchinson trace estimator. Okay. Then what we need to do is to basically take these random perturbations and then sort of try to approximate what the Hessian would be. Okay. So again, what's the definition of a derivative? So we say that the derivative of a function is proportional to, let's say, f of x plus some delta minus fx divided by delta for some small delta. Okay. So in this case, I want to calculate the Hessian, and Hessian is basically the derivative of the gradient. So f will be the gradient. That's why here I use basically the gradient at two different points. One point when I basically take the original image, minus the other point where I perturb the image with some random perturbation. Okay. So long story short then, using some nice results from linear algebra such as Hutchinson trace estimator, as well as zero-order gradient estimation, we can find a good reliable approximation of the curvature. So that means that we kind of have an answer to our first question about computationally efficient proxies to memorization. Okay. Also, thanks to this notion of sensitivity, we can think of curvature as a way of talking about second-order sensitivity. So curvature depends on Hessian. Hessian is a second-order quantity. So what we are doing, we are performing a second-order characterization of the sensitivity of our model with respect to changes in the data. Okay. So why not use other orders? For instance, first order or zero order sensitivity. Okay. So that means that instead of for instance, the Hessian and its trace, why not use the input gradient and its norm to characterize sensitivity? Or even zero order notions of sensitivity. Basically means that you look at the loss value to characterize sensitivity and therefore find a good efficient proxy to memorization. Okay. And yeah, so there is nothing that stops us to actually use these ideas, and also their cumulative versions for potentially more affinity and with memorization. So therefore, we can talk about a broad family of what I refer to it as differential input sensitivity. Okay, so differential basic because we are using notions of derivatives such as gradient and Hessian to talk about sensitivity. Input sensitivity because we are talking about the sensitivity of our loss, sensitivity of our model with respect to the input, not the parameter. Okay. And I would say that there is an active area of research to basically study the relationship between these different proxies, determine which one is more useful in which scenarios, etc. Okay. One potential benefit of differential input sensitivity is the ease of studying memorization in context beyond supervised learning. So for all of the lecture about memorization, we basically focus on the setting of supervised learning, where our data is basically a collection of features and labels. For that, we had this elegant definition of memorization. And then we talked about this, the importance of memorizing long-tail samples to make sure we have good generalization. Okay? But how can we go beyond supervised learning? Okay? What if I don't have any labels in my training data? What if my learning setup is not even like classification or clustering, rather is something like a reinforcement learning? Okay? And a benefit of differential input sensitivity is that we could potentially study memorization in other contexts. For instance, unsupervised learning and generative models. Okay? Because all we need is basically, let's say, the derivative of the loss with respect to the input. So I don't care if my input is a collection of features or labels. As long as I can calculate this derivative, I can characterize sensitivity and therefore potentially relate that to the memorization of my deep learning model. And I mentioned that this is indeed an active area of research to talk about the memorization phenomenon in various deep learning paradigms. And finally, let's also talk a little bit more about distinguishing between noisy and hard examples and another potential benefit of differential input sensitivity. So here we've tried to visualize basically the loss values, which again we can think of it as some notion of differential input sensitivity for both typical and atypical samples. Okay. So here we are basically showing these results. So basically we want to see how the loss evolves throughout training for different kind of samples. So here on the left panel, we are talking about the evolution of the loss for an easy typical sample. Here we are talking about the evolution of the loss for a hard example, so a truly atypical example. And in this case, basically we are talking about the evolution of loss for a duplicated or mislabeled sample, essentially a noisy sample. Okay. Now, from this empirical study, we can make a few observations. So first of all, when I look at the final loss value, both typical and atypical examples exhibit a low loss value. Okay, so as we can see here. So for instance, the loss value here is roughly 10 to the minus 3 for the simple example. Same for the atypical example. It's roughly 10 to the minus 3. Okay. On the other hand, for noisy samples, the final loss remains relatively high. So as we can see here, for a noisy sample, the loss is hovering around 0.4 or something. Okay. So that's the first observation. The second observation is about the average loss or the cumulative loss throughout training. So the observation we make here is that the average loss for a typical sample is actually low. For instance, the average loss here, which I'm demonstrating with this red curve, is near 10 to the minus 1 for a typical example, whereas for both atypical and noisy sample, the average loss remains very high. So as you can see here, for a hard example, the average loss is again around 1. Same for a hard noisy sample. So we can combine, therefore, we can leverage these observations and propose a metric that not only looks at the final loss value or final differential input sensitivity, but also the cumulative differential input sensitivity, with the hope of distinguishing between hard as well as atypical examples. In particular, we can propose the following notion, let's call it good memorization, which is the difference of, let's say, cumulative differential input sensitivity and final differential input sensitivity. When this difference is basically high, this basically means that the average is large, but the final is low. So based on this observation, it is indicating an atypical example, a hard example. And when this is near 0, based on this observation that we are seeing here, both the cumulative differential input sensitivity and the final one are basically of the same order. So it should indicate a hard, noisy example. Okay? So therefore, this is another potential benefit of differential input sensitivity. Not only that is a computationally efficient proxy to memorization, but also it can help us to design criterion that could potentially help us to distinguish between samples that are essential to be memorized versus samples that are not because they are noisy. So this is the sort of the end of our lecture on memorization as one of the contexts that we need to care about when training deep learning models. In the next lecture, we're going to talk about another context, which in some sense is also related to both memorization and privacy, and that's the concept of robustness. I'll see you in the next lecture.